Okay, so as we move on, I want you to think back to when we first came across discrete random variables and actually all of the distributions we've worked with. One of the first properties we tried to find were the expectation and the variance. And so I'll quickly run through a reminder of how we calculated the expectation. It was the outcome multiplied by the corresponding probability, each time all the way through until we've covered all of the corresponding pairs. We also found the expectation of x squared by using the outcome squared multiplied by the probability, etc. all the way through. And we derived and came across a relationship for the variance. So the variance of x was the e of x squared subtract the e of x squared. So hopefully that's a reminder and you're quite comfortable with what we've done there. If I go ahead and find the numerical values, we see that e of x is 2.3, e of x squared is 6.1, and then combining them in the variance formula, 6.1 minus 2.3 squared equals 0.81. Well, since we're working with probability generating functions, which we realize are just another way to demonstrate a discrete random variable, we would also want to be able to find these properties while it's in its PGF form. So we're going to try and go step by step and deduce each of these properties: the expectation of x squared, and the variance of x, all for use while our probability distribution is in PGF form. So these are the numerical values, but let's go for something a bit more generalized. So the expectation of x will always be the sum of the x values multiplied by the corresponding probability. Expectation of x squared will always be the sum of the x values squared and then multiplied by the corresponding probability. And the variance of x, once again, is just going to be e of x squared minus e of x squared. So if you do think back to when we first introduced probability generating functions, we did say that because it's in the polynomial form, there are some things that we can do with it that we should be quite comfortable doing with polynomials. So one of the first things I think we should be able to do is to differentiate. So we can differentiate, but in what way would it be useful? Let's find the first derivative of this probability generating function. If I was to differentiate, I would get 0.1 plus 2 times 0.7t plus 4 times 0.2 t cubed. You may not recognize anything in this at the moment, but what would happen if we substituted in 1 instead of the t? Well, we would get all of our coefficients. So 0.1, 2 times 0.7, and 4 times 0.2. Well, do you recognize what we have here? This is the expectation of x. We've got 1 times its probability, 2 times its probability, and 4 times its probability. The first derivative of the probability generating function with a 1 substituted gives you the expectation of x. So you can see that in this example that we've been using all the way through, but obviously we would like to see if we could generalize that. So let's have a look at a way to get to the same conclusion through generalization. This time let's describe the probability generating function how we did previously as the sum of the dummy variable multiplied by the corresponding probability. I am going to make an assumption here that we have consecutive values of x starting at 1, and I'm going to generate each of the terms that we should get for this. So the probability that x equals 1 multiplied by t to the power of 1. Probability that x equals 2 multiplied by t to the power of 2. X equals 3 multiplied by t to the power of 3, and so on and so forth. So this is my expression for the standard probability generating function. So it's not differentiated just yet. What would I get for the first derivative? So differentiating with respect to t, bring the power down and multiply by the coefficient, reduce the power to get t to the power of 0. Bring the power down, 2 becomes the coefficient, multiplied by the probability, reduce the power, it's t to the 1. Here I'm going to get 3, probability statement, t to the power of 2. 4, probability that x equals 4, t to the power of 3. And what would happen if we were to substitute 1? We're basically eliminating the t variable, because obviously 1 to any power is going to be 1 and it doesn't need to be written within its product. So we would end up with just the coefficient multiplied by the probability. And that's exactly what we're looking for the expectation. The outcome, or the x value, multiplied by its corresponding probability. And that's what we get for gx of 1. So a couple of ways here I'll try to demonstrate or convince you that g dash x of 1 equals the expectation of x. We'll look at this through one more lens, and that will be for us to try and see if we can prove the expectation for a Poisson distribution is indeed meant to be lambda. So when we first were introduced to the Poisson distribution, I'm sure I showed you quite a long-winded proof of how we ended up having lambda as the expectation, and I told you at the time that you weren't necessarily meant to understand that. I'll put that on the screen after and see how we can compare it to the probability generating function technique of proving the expectation should be lambda. So let's just start by defining the distribution. X follows a Poisson distribution. The only parameter is lambda. We'll get that in there. We've seen previously that the standard probability generating function for a Poisson distribution is e to the lambda multiplied by t minus 1. So we covered that in the previous section. You can go back and recap if you want to. Let's see what we get if we were to differentiate. So we're trying to find g dash and substitute in 1. So g dash is going to equal lambda e to the lambda t minus 1. Okay, so that's how we differentiate with an exponential. Let's substitute in the 1 and see what happens. Well, straight away I can see that the power on that exponential is going to become 0. I'm going to have 1 minus 1 in the bracket. E to the 0, anything to the 0 is 1, which leaves us with just lambda. So if g dash of 1 equals the expectation, then the expectation here does indeed equal lambda. Let's compare that to the standard proof. Okay, moving on to trying to find the variance, there are actually quite a few steps that you need to be quite happy and comfortable with to really understand what's going on. Make sure that you pause where appropriate so that you can absorb exactly what's happening at each stage of this working out. So we'll pick back up at this first derivative of the probability generating function, and we'll continue to find the second derivative. So we're going to differentiate the right hand side and let's see what happens and if we can recognize anything. Well, bringing down the power of 0 here is actually going to give us a 0 coefficient, which means that the whole term itself is going to be 0. So I'll just skip this and move on to the next one. So bringing down the coefficient of 1 and reducing the power to 0. Bringing down the coefficient of 2 and reducing the power to 1. Bringing down the coefficient of 3 and reducing the power to 2. So you may not be able to see anything at this stage. Let's substitute in a 1 instead of the t variable. So when we substitute in a 1, we get 2 times the probability x equals 2, 6 times the probability x equals 3, 12 times the probability that x equals 4. Now we may not be able to see anything or any sort of pattern happening at the moment, but the numbers 2, 6 and 12 do actually have something in common. Each of them are factorials. We have 2 factorial, 3 factorial and 4 factorial. Let's look at it in a more generalized form. So I'm once again going to start with the definition of a probability generating function, which says that it's the sum of a dummy variable multiplied by its associated probability. Well, what would I get if I was to differentiate this? So g dash in this case, well, I'm differentiating with respect to t. So I'm going to bring down the power from t and make it a coefficient, reduce the power by 1, and multiply by the probability statement. The second derivative, well, I'm once again going to bring down the power, the x minus 1, scale that into the coefficient, and reduce the power by 1. So it becomes x minus 2, and multiply by the probability again. Do you recognize anything in any of these statements? It's probably more useful to substitute in 1 to each of these, and let's see what that generates for us. So gx of 1, we've seen this before, is actually going to be the sum of all of the probabilities, and we know that they should all sum to 1. G dash of 1, well, we're going to eliminate the t variable, and we'll be left with the sum of x multiplied by the probability statements, which indeed is our expectation. What will happen for the second derivative? If we substitute 1, we do eliminate the t variable, the t term, but what do we leave in its place? We get the sum of x multiplied by x minus 1 multiplied by the associated probability. You might recognize it from this point, but I'm going to go ahead and expand. So let's multiply the x and the x minus 1, and I'm going to take it one step further and see if you can start to recognize what we have. We expand those brackets on the inside of the summation. We then get the sum of x squared multiplied by the probability, subtract the sum of x multiplied by the probability. Each of these we should actually recognize. This first one is the expectation of x squared, and the second one is the expectation of x. Okay, so let's just take a second there. So the second derivative of the probability generating function when we substitute in 1 will give us e of x squared minus e of x. Okay, so we have a little bit of baggage here, maybe more than we were expecting from that expression. We were expecting something to do with the x squared, but it's brought along something which is just the e of x. But not to worry, we can still make something of this. For both of these expressions, I'm actually going to try and make e of x the subject in the first one and e of x squared the subject in the second one. Well, since I now have an expression for the expectation of x and an expression for the expectation of x squared, I should be able to make use of that familiar variance formula. So the variance of x is a combination of the two, is the expectation of x squared subtract the expectation of x squared. Let's see what happens as we start to substitute into this expression. So e of x squared first, I get the second derivative of the probability generating function with 1 substituted in, plus the expectation of x, and then I'm going to subtract the expectation of x squared. Well, I have an expression for the expectation of x. It's the first derivative of the generating function with 1 substituted in. So it's g double dash plus g dash subtract g dash squared. Okay, so it took a while for us to get here, but this is the formula to use when finding the variance of a probability generating function. We're going to need to use some calculus and this combination. You're not on your own. This formula is given to you in the formula book, but obviously we would like to know how to derive it. Just as you've seen with the majority of formulas, that with adequate practice, no doubt you will be able to commit this to memory. As we move on, let's just see how we can use these two properties within problem solving. So how can we solve problems that ask us to find the expectation of x and the variance of x? We'll go through a couple of examples and then I'll let you get down to some of your own individual practice. So here in this example, we've been given the definition of the probability generating function, and it's 1 over 100,000 multiplied by 9 plus t squared all to the power of 5. we've been asked to find the expectation and the variance. So we're going to use the formulas that we derived earlier on. So to find the expectation, I know that I want the first derivative of the probability generating function. So if we're going to do some differentiation here, we need to look out for the fact that we have the chain rule that needs to be applied. Okay, so let's go ahead and find g dash of the function. So I'm just going to ignore the coefficient, the 1 over 100,000. That's going to be in place regardless. And let's just apply the chain rule over here. Bring down the power, multiply by the derivative of the bracket, reduce the power of the bracket by 1. Okay, let's do a little bit of tidying up. Let's see if we can make that a little bit neater. So I've got 10t over the 100,000. That can cancel out. And then we've got our bracket here. Okay, now that I found an expression for the derivative, I know that I should just substitute 1, and that will actually give me the expectation. So when we substitute in 1, we get 1 over 10,000, and we get 10 to the power of 4. Okay, this is actually looking quite nice, because 10 to the power of 4 is 10,000. So 10,000 over 10,000, numerator and denominator match, this is 1. The expectation of x, the expectation of this probability generating function is 1. Okay, so on the way to finding the variance, I know that I want to find e of x squared. So let's just go ahead and remind ourselves, e of x squared was g double dash of x plus g dash of x. So I've already got the first derivative, I need to find the second derivative to make use of this. So let's go from here. A reminder, the first derivative actually is now a product of two functions. So I am going to need to use the product rule while I'm differentiating. So I've got 1 over 10,000, it's coefficient, I'll leave that out for now. And I've got t as one of the variables, or one of the functions, and this bracket to the power of 4 as the second function. Alright, so let's just quickly define those. So the first function u is t, second function v is 9 plus t squared to the power of 4. Okay, differentiating t, we get a value of 1, du dt is 1, and differentiating v, we get 4 times the derivative of the bracket multiplied by the bracket to a reduced power. Okay, dv dt is, if we were to simplify, 8t 9 plus t squared to the power of 3. Actually, this should be g dash. Okay, so from here I'm looking to compile the second derivative. As I said, I've taken the coefficient, the 1 over 10,000, outside. So I'll just write that outside of some square brackets. And I'm going to go with the product rule. And I'll do v multiplied by du dt. So that's the original bracket multiplied by 1, plus u multiplied by dv dt. So it's going to be t multiplied by the 8t. So I'll get 8t squared. And then my bracket to the power of 3. Okay, we can definitely neaten this up and try and see if there's any opportunities to simplify. So the bracket is a common factor between the two of them. So I'll factorize out the bracket. I have the bracket to the power of 3 is common, leaving me with a 9 plus t squared and an 8t squared. Okay, this second bracket neatens up quite nicely. I'm going to have 9 plus 9t squared. I do have opportunity to simplify, so I'm going to take the 9 outside of this second bracket. So I'm just going to factorize here. And I think this is as simple as I can get for now. This is going to be the second derivative. So 9 over 10,000, 9 plus t squared to the power of 3, 1 plus t squared. If I substitute 1 into here, g double dash of 1 is going to equal 9 over 5. So getting to this point did rely on some good calculus skills and definitely some good algebraic manipulation. Let's move forward. So my e of x squared is g double dash of x plus g dash of x, both with 1 substituted in. So that's going to be my 9 over 5 plus 1, which altogether gives me 14 over 5. Now I'm ready to use my variance formula, my original traditional variance formula, the one that I've committed to memory from a long time ago. And I'm just going to substitute in my e of x squared value and my e of x value and make use of the formula. So it's 14 over 5 minus 1 squared, which takes us back down to 9 over 5. So the variance of x is 9 over 5. Okay, once again, this question in particular relied on some good calculus and some good algebraic manipulation, neither of which are actually taught in this further statistics unit or this further statistics course. These are prerequisites. We're expecting, and the examiner is expecting, that you come to the table with these skills already. I suppose I'm encouraging you against compartmentalizing these different skills. Applied maths is expecting that you're very strong on pure and that you can bring those skills into applicable situations. So in this example, we've been given a very generic looking probability generating function, but we have been told the expected value of x and the variance of x. So we know something about it. So let's go ahead and see if we can get it into a form that represents the e of x, the expectation of x. We're going to go for the first derivative, which is b plus 2ct. We know if we substitute 1 into this, that should give us the expectation. So b plus 2c should equal the expectation given in the question, which is 7 over 6. Okay, let's hold on to this. This will probably be useful later on. I'm just going to box it off for you. And we're going to move on to trying to find the variance. Well, the variance we know is going to use the second derivative, so let's just go ahead and try and find that. Differentiating again will just give us 2c. Okay, g double dash is 2c. Well, the expectation of x squared is g double dash plus g dash. So it looks like it's going to be 2c plus the expression we already had before, b plus 2c. Okay, I could at this point probably substitute the 7 over 6, but I'm going to keep it in these unknowns so I can start combining. Combining them together, we get b plus 4c. Okay, I know something about the variance, so let's try and get an expression for the variance in terms of b and c. The variance of x is the expectation of x squared subtract the expectation of x squared. Okay. So through that substitution, we should get b plus 4c minus 7 over 6 squared equals 29 over 36. So I can see from here that actually I'm going to generate a second equation in terms of b and c. So let's just try and get the constants over to the right hand side. I'll start by squaring the 7 over 6 and then adding that to both sides. b plus 4c equals 78 over 36. Okay. I have two equations in two unknowns, so simultaneous equations here will help me to solve for b and also to solve for c. This is just going to go straight into the equation solver on the calculator, so I will get b equals 1 over 6 and c equals negative 1/2. Alright, so all that's left now is to find a, and I'm going to go back to the original probability generating function, and we know that in this case gx of 1 should equal 1. So substituting in my b and my c, without even using the calculator, this should be some simple arithmetic. A sixth plus a half is 2/3, so a must be 1/3. And there we have it. We found a, b and c. A is 1/3, b is a sixth, and c is negative a half. Okay, so using the first and second derivative of the probability generating function with a 1 substituted in, we should be able to find the expectation of x, the expectation of x squared, and also the variance of x. You can either use the technique that I've done, where I'm finding e of x squared and I'm finding e of x, and then making use of them in a formula that we're very familiar with within further maths, or we can just use the formula in pure terms of the second and first derivative, g double dash plus g dash minus g dash squared. Okay, this is given to you in the formula book. The original equation I do think you should be quite familiar with, and it's something you've been using for so long that potentially that's the route you should take.